Hi everyone, welcome back to Math 320 videos. This week we will take a little bit of a break and have a bit less recorded content in anticipation of and in honor of the US general elections. Even in face of the reality that I can glimpse from YouTube channel statistics, I still hope one or two of you will be watching this before election day. If so, can I remind you to go vote if you haven't done so? Okay, back to our scheduled programming. This week, we will continue our journey last week toward understanding continuous functions. Last week, we defined the notion of limits for functions, and then through that lens, we introduced the epsilon delta definition for the continuity of a function. In this week, we will explore some properties of continuous functions. Our main goals are two classic theorems on continuous functions, the extremal value theorem and the intermediate value theorem. Prior to presenting those two theorems and their proofs, we first complete our introduction to continuous functions by briefly discussing some basic properties of continuous functions, continuing on the theme of limits. The material covered in this lecture are also included in your textbook on pages 128 through 130. An important theorem concerning continuous functions is that continuity are preserved under function composition. In other words, compositions of continuous functions are again continuous. A more precise statement is shown on this slide here. We let f and g be functions and suppose f of c is equal to gamma. If we suppose that f is continuous at c and g is continuous at gamma, we get the conclusion that the composite function g composed with f is a function that is continuous at c also. In the theorem statement, we assume that g has domain all of real numbers. If we know that f has a more restrictive codomain, say a set t, and that g has domain t, then the same theorem holds also. The proof of this theorem is pretty simple. Again, this is an illustration of passing the buck. To prove that g composed with f is continuous using an epsilon delta argument, what we do is use the continuity of g to obtain an intermediate delta sub g, and then use the intermediate delta sub g as an epsilon for f, and use the continuity of the function f to get the final delta. One way to understand this is to think back to the description of continuous functions in terms of tolerances. Remember that a function is continuous if, for any required or prescribed tolerance epsilon downstream, we can specify a tolerance delta upstream, so that if the input is within delta of the requirement, we can guarantee that the output is within epsilon of the requirement. Now, the function g composed f is the result of first applying f and then taking its output and plugging it into g. So, to control the output of the composite function, we take the requisite tolerance epsilon of the final output and show it to the function g, which says that it can guarantee the tolerance provided the input it receives is within the intermediate tolerance delta sub g. Since f is to the upstream of g, this information is relayed back to f, which then decided that its input tolerance must be based on this information. The proof on this slide formalizes this concept. Let's go through it. Start with epsilon positive. Since g is continuous at gamma, we know that if the input to g is within some delta sub g of gamma, the output of g will meet our requirement and about being within epsilon of g of gamma. To guarantee the input of g is within delta sub g of gamma, we use that gamma is equal to f of c, and that f is continuous c, which means that there is some delta sub f such that if the input to f were within delta sub f of c, the output of f will be within delta sub g of f of c, or gamma. Chaining this together, we see that if the input to f is within delta sub f of c, the output will be within the tolerance required by g, which means that the composite output will then be within epsilon of g of f of c. And since epsilon is arbitrary, this shows that g composed f is continuous at c. The nice thing about this theorem is that it allows us to build more complicated continuous functions out of simpler parts. For example, let's accept for the time being that the absolute value function, the sine function, and the cosine function are all continuous functions on the entire real line. Then, for any continuous function f, we find that the absolute value of f, the sine of f, and the cosine of f are all also continuous functions. In many settings, by dividing up a function into a composition several layers deep, the continuity of each individual layer can be easier to prove algebraically, compared to trying to prove that a function is continuous using the epsilon delta argument applied to the whole composite mess. Here's an example with more restrictive domains. Notice that the square root of x is a continuous function on its domain, which is the set of non-negative real numbers. So, if f is a continuous function whose output are always non-negative, then the square root of f will have to be also continuous. Similarly, noticing that 1 over x is a continuous function with domain all of the real numbers except for 0, we know that if f is a continuous function whose output is never 0, then the function 1 over f is also continuous, thanks to this theorem. Let me just mention here also the following theorem on arithmetic. We will skip the proof of this theorem. The proofs are essentially the same as the cousin theorem, which gives the same results for limits of sequences. It basically says that sums and products of continuous functions are continuous. Okay, that's it for this lecture. See you next time.